In this video, we will be discussing the dynamic system of an aircraft's autopilot and the effects of the elevator deflection has on the pitch of an airplane. A pitch motion is the up or down movement of the nose of an aircraft. This motion is caused by the deflection of the elevator of the aircraft. Changing the angle of deflection at the rear of an airfoil changes the amount of lift generated by the airfoil. With greater downward deflection, lift increases in an upward direction. With greater upward deflection, lift increases in the downward direction. The coordinate frame involved in the dynamics of the system are the inertial frame, denoted by x' and z' axis in the figure, and the body coordinate frame, denoted by the x and z axis in the figure. The various symbols in the figure are as follows. Theta is the pitch angle of the aircraft. Alpha is the angle of attack, as seen at the tail of the aircraft. Delta is the deflection angle of the elevator. In order to simplify the pitch motion of an aircraft, we will make a few assumptions. First, the aircraft is at steady level flight at constant altitude and constant velocity, therefore balancing the thrust, drag, weight, and lift forces in the x and y directions. Second, we will also assume that the change in the pitch angle will not change the speed of the aircraft.
Under these assumptions, the equations of motion for the aircraft look like this. The rate of change of alpha is equal to the force in the z direction due to alpha times alpha, plus the force in the z direction due to q times q, plus the force in the z direction due to delta times delta, all divided by mass times free-stream velocity plus q. The rate of change of q is equal to the moment about y due to alpha times alpha, plus the moment about y due to q times q, plus the moment about y due to delta times delta, divided by the mass moment of inertia about y, and the rate of change of theta is equal to q. In order to obtain a desired pitch angle, an airplane's autopilot employs a discrete feedback loop. The feedback controller responds to a step command of the desired pitch angle. The elevator deflection angle, delta, is then inputted into the transfer function of the system. The output is a pitch angle, theta, which is then compared to the desired pitch angle and deemed usable depending on the steady-state error. In order to optimize the system's performance, we want to minimize the steady-state error in order to achieve the desired pitch, minimize overshoot to prevent too large of a pitch change, and finally, minimize rise and settling time so that the system can adjust to new inputs without delay. Here's a recap of our dynamic system. Thanks for watching.